Hey, just a quick public service announcement before we get started. It's November, which is a month typically we try to raise awareness for men's health issues. We often do this by trying to grow a mustache. So it's been a few days, and we'll see what happens by the end of the month. I'm a little nervous. But if you're a man and you're over the age of 50, go to your doctor, get checked out. It's important. If you know a man who is reticent about going to the doctor to get things checked, I can totally relate to that. Still, recommend to them as much as you can, advocate for them to go get checked, especially if they're over the age of 50. For more information, you can go ahead and check out Movember.com. They've got a lot to say there. Okay, on with the show.
We've been talking about the Stern-Gerlach experiment a lot, and last time we talked about it in the context of quantum information, and we built out circuits, or toy circuits, if you like, of multiple Stern-Gerlach experiments chained together. One of our examples that we gave turned out to be an error, and we only discovered this error after publishing the video. Unfortunately, explaining why we were in error requires a lot of technical mathematical machinery to really get that point across. Fortunately, we are at a point now where it is time to learn the technical mathematical machinery associated to quantum mechanics. So today, we are going to explain why we were wrong and what the true answer is in this video by explaining to you some of the precise technical mathematics involved in quantum mechanics. Let's get started. In our previous discussion, we spent a lot of time working with the three-machine circuit, that is, three Stern-Gerlach devices connected together with the usual inputs and the usual outputs. And we have the freedom to choose the orientation of the individual magnets inside each of the devices. Specifically, we focused a lot on the case where, for example, we had Z orientation for the first device and X orientation for the second device, and again, the Z orientation for the third device. In our original traditional setup, when you put a beam of silver atoms through this circuit, the output is a split beam, evenly split, on the detector screen. One of the examples that we showed involved turning off that second detector completely, just basically removing it in some sense. And that caused the three-machine circuit to reduce effectively to a two-machine circuit, from which silver atoms would enter the first Z machine and then travel through the second machine with nothing happening and enter the third Z machine, which means that the only particles that would enter the third Z machine were already spin up in the Z direction. So the final output was spin up completely. In other words, one beam. Turning on or off that second device effectively changed the output of the circuit from a split beam to a single beam and then again back to a split beam. We tried to set up a conceptually more complicated, although somewhat similar example where instead of turning off the second device, we tried to circumvent it. Specifically, we tried to avoid measuring which output the silver atoms went through. We refocused both beams together back into a uniform beam and inserted that beam back into the third device. And in case there was any confusion about what we were doing, we really wanted to emphasize the fact that we were not taking a measurement. The experimenter would not know which output terminal the silver atom went through. And to accentuate that fact, we added the capacity of adding these little clickers on either terminal so that if a silver atom went through the up, it would make an up click sound, and if the silver atom went through the bottom, it would make a down click sound. This is admittedly a contraption. It's something that's not easy, certainly for experimentalists to do, but what we're trying to do is probe the theoretical details of quantum theory in a kind of a cartoon experiment, which is what all of this is. It's a learning experience. Unfortunately, by doing this process, we ended up confusing ourselves as well and made an error. We said that in this situation where we do not know which terminal the silver atom went through, the final output would be up. Just like turning on or off that second device, as if that second device wasn't there. Unfortunately, this is completely wrong. We were 100% wrong. In fact, the actual answer is literally the opposite of this. That is to say, in this case, where we circumvent the second device but do not turn it off, so its magnetic field is still there, what would actually happen is the beam of silver atoms would, in the final detector screen, be pointing 100% in the down direction. Weird, right? Today, we're going to learn precisely how to show that this is true in this hypothetical cartoon toy model experiment. Nevertheless, it has the important lesson that says measurement is important in quantum mechanics, and just because something wasn't measured didn't mean something didn't happen. So let's dig into it. We have been sprinkling in a little bit of the mathematical details involved with quantum mechanics over the course of these videos. And today we're going to collect them all and really define precisely what we mean when we talk about the mathematics. So you might recall that the most general quantum state of a silver atom, from the perspective of the measuring device, like a detector, is a two-level state. Those silver atoms can either be spin up or spin down with respect to some detector. We parameterize these with two constants, alpha and beta, and wrote it in this funny vector language here. That is to say, the silver atom vector is equal to alpha times spin up plus beta times spin down. Now, as we've seen before, there's another way to repackage this information that's a little bit easier to use in other contexts, and that is using a column vector. So we can represent this vector notation, if you like, in a slightly different way. That is to say, in a column where alpha takes the first component and beta takes the second component. The idea here, of course, is the mod square of alpha is the probability of finding that silver atom in the spin up state, and the mod square of beta is the probability of finding that silver atom in the spin down state. And so the two unit vectors in this column vector notation, with the one in the upstairs corresponds to spin up, and the one in the downstairs corresponds to the spin down state. Today, we are going to make extensive use of this column vector notation. And also, when we take inner products, we'll be using not only columns, but also rows. And we talked a little bit about this, but just to refresh your memory, if I have two such vectors, let's call them psi and phi for cultural reasons, if you like, we can take the inner product of phi with psi, and that is given by taking a row vector and multiplying it by a column vector, right? So in other words, we take phi as our row vector, and we just smash them together. That's just how the mathematics works. Right, so you take the two components of the column vector and you smash them on top of the two components of the row vector, or vice versa, however you want to think about it. The point is, the rule is it looks something like this. Now, remember, those little stars there are associated to complex numbers. If that bugs you, you can ignore them. We can pretend that they're not there, at least for now. The point of all this is you might recall that the inner product of a vector with itself, let's say that AG vector with itself, right, would tell us that the row part of AG multiplied by the column part of AG gives us what we expect. The first two components of each multiplied together, alpha star alpha, mod A squared, and plus beta star beta, mod beta squared. And again, one more time, remember that the probabilistic interpretation of these quantum state vectors, of finding which state that they're in, right, requires that the sum of these two mod squared quantities, alpha squared plus beta squared, must be equal to 1, or 100%. Okay, enough about vectors. Now let's talk about observing those vectors. The kick that those silver atoms received from the magnet inside the Stern-Gerlach device depended upon not only the orientation of that magnet, but also the orientation of that silver atom, whether it was spin up atom or a spin down atom. Whatever, we talked about this a few videos back. Because the spin angular momentum of silver atoms are restricted by the rules of quantum mechanics to be observed either at 0 degrees or 180 degrees, either at spin up or spin down. That means that the kinds of kicks that the Stern-Gerlach device can impart upon any given silver atom are equal in magnitude but opposite in direction. That is to say, we can package all that information about the force, whatever the details are, as some constant. Let's call it little sigma. So the force experienced by a silver atom will always be little sigma up, that is to say parallel to that magnetic field, or little sigma down, that is minus little sigma, anti-parallel to that magnetic field. So little sigma here is the magnitude of the impulse that's experienced as the silver atom flows through the Stern-Gerlach device. Mathematically, a convenient way to represent the action of the Stern-Gerlach device on that vector that we had, right, with alpha and beta, can be represented as a matrix. And since only two things can happen, the matrix is really straightforward. It's a diagonal matrix, and the two components are going to be sigma and minus sigma, so that if it's a spin up state, it's going to hit with a sigma up. If it's a spin down state, it's going to get hit with a minus sigma, or a kick down. In mathematical terms, the precise definition of quantum mechanics, if you like, the detector that we're discussing, the Stern-Gerlach detector, is the matrix. That's the map between what we're talking about, this cartoon, this experiment, and the mathematics, the formalism, if you like, of quantum mechanics. The detector is the matrix. The matrix, this operator that acts on the state vector, is what we mean when we talk about an observable, mathematically speaking. It's worth pointing out that everything that we have to talk about today, we will be talking about from the basis of vectors in the z direction. So we're always have in mind this matrix, this vector, up and down with respect to a z Stern-Gerlach experiment. But that doesn't mean that we can't talk about other directions of the Stern-Gerlach experiment. For example, the matrix associated to a Stern-Gerlach device orientated in the x direction in this basis is given by another matrix, a different matrix, a matrix that is kind of almost maximally different. That matrix is given here. That is to say, it's got ones in the off-diagonal elements of the matrix and zeros along the diagonal. That's the operator that corresponds to a Stern-Gerlach device which is orientated in the x direction. Cool. Not being diagonal, this thing is slightly more complicated to interpret. But again, that's the price we pay for using a z basis and asking questions about the spin of a silver atom in the x direction. Nevertheless, we can compute the action of that matrix on the up and down vectors. And this is what we get. So if we take this sigma sub x matrix and act on a spin up in the z direction vector, what do we get? Oh, it flips the spin. The spin goes from up to down. Similarly, if we act on a spin down vector, what do we get? Oh, it also flips the spin. The spin goes from down to up. Interesting. So under the influence of this spin x operator, this sigma x, the spins flip. At least the spins in the basis of the z direction. So perhaps now you can begin to understand why we made that error in the last video. Maybe, but not so fast. Quantum mechanics also says that we can only measure with respect to the measuring device. So if we have a Stern-Gerlach device in the x direction, and we're going to measure the silver atoms, the only possible states that come out have to be spin up or spin down in the x direction, not the z direction. So from that perspective, what does this operator, sigma x, acting on an up or down state in the z direction, what does that even mean? Great question. To understand what that means, let's go back to the more familiar case, the diagonal case, the sigma sub z case, the Stern-Gerlach device in the z direction. And let's review one more time what happens with those spin up and spin down vectors. So when we have that matrix acting on a spin up vector, we get the spin up vector itself back with a constant out in front, and that constant is just sigma. Similarly, with a spin down vector, we get another constant out in front, but that constant's a different constant, it's minus sigma. But we get that we get that vector back. Contrast this with the application of that sigma x, that x Stern-Gerlach device matrix, right? And we don't get the same vectors back. We get a different vector back. It's a completely orthogonal direction in this instance. So there's a difference of behavior there. When the z matrix acts on a vector in the z basis and gets that same vector back, effectively all we've done is multiply by a scalar. It's the same thing. This is a very special phenomena. In general, whenever a matrix acts on a vector and gives you that same vector back, perhaps with a constant out in front, we call that vector an eigenvector. And we call that associated scalar out in front an eigenvalue. These are German terms because German folks invented the mathematics. But generically, given a matrix M, the search for a vector v that behaves like m times v is equal to some constant lambda times v, the search for v and lambda given a matrix M is sometimes called the eigenvalue problem. And for n by n matrices M, there will be at most n eigenvectors, and therefore associated with n eigenvalues. For the case of sigma z, those eigenvalues were easy to see, right? They're just the diagonal components, and those eigenvectors are just the spin up and spin down states. In some sense, this is not a conspiracy. This is using the correct basis of vectors. We will learn to use eigenvectors and eigenvalues a lot because they are intimately related to the physics of quantum mechanics. To make sure you understand what is going on, let's do an exercise. Write down any diagonal matrix you like, M, in any number of dimensions. So a diagonal matrix is just a matrix that only has non-zero components along the diagonal. You should be immediately able to write down every single eigenvector of that matrix and tell me what the eigenvalue of that matrix is with respect to that eigenvector. It should be no problem. To reiterate just how important these eigenvectors and eigenvalues are to quantum mechanics, let's talk about some fun mathematical facts in quantum mechanics. These fun math facts are going to be the rules which we carry forward in the study of quantum mechanics. So, without further ado, fun mathematical fact number 1. Every single measurement that can be made in quantum mechanics, every single observation is associated to an operator that acts on the quantum state vector. If that quantum state vector happens to be a finite dimensional vector, like our silver atoms, then that linear operator is just a matrix. To reiterate, operators are observables. Mathematically, observables are operators, matrices. Cool. Next, math fun fact number 2. For every observable operator, say M, the actual observations that can be made in quantum mechanics correspond to the eigenvalues of that matrix, of that operator. Eigenvalues are the only possible things you can observe. Remember, when it comes to spinning objects, we have a finite resolution of the information carrying capacity, right, of those physical objects. That finite resolution is associated to the eigenvalues of the operator that's doing the observation. Cool. Now, math fun fact number 3. When a measurement is made in quantum mechanics, the state, the physical quantum state vector, changes. And it changes to the eigenvector associated to the eigenvalue that was observed. So if we observe the eigenvalue of a silver atom that is spin up, then the vector, the quantum state, is changed to spin up. Similarly, if it's spin down, then that quantum state vector is changed to spin down. To reiterate, quantum mechanics changes the physical state of a quantum system to correspond to the eigenvector that's associated to the eigenvalue that was observed. That's the process of measurement. Awesome! But there's more. Math fun fact number 4. As far as we can tell, nature selects that eigenvalue, that eigenvector, at random. And the probability distribution for that choice that nature makes is associated to the quantum state vector itself. Just like for the case of the silver atoms, right? You have alpha and beta. Mod alpha squared is the probability of finding it spin up. Mod beta squared is the probability of finding it spin down. But up and down are the only two options. And so once measurement happens, it's going to pick one or the other. Okay. In some sense, that's the mathematics of quantum mechanics. Of course, we will learn more about it with more context and more examples in more videos down the road. And it might just seem like a bunch of obscure mathematical facts at this point. Perhaps, but no doubt you've already studied them at length in the context of silver atoms. So, as our second exercise to make sure that you understand what's going on, please reframe these fun math facts in the context of the silver atom. Measurement is the weird part of quantum mechanics. Nobody knows exactly how the universe chooses to pick one quantum state vector or another, or how that transition of the state vector to an eigenvector works. As far as we can tell, it happens totally randomly. That's just how nature works. Our job is to describe, of course, how nature works. But why it works is hopefully clear. We can't measure something physically as a linear superposition of two distinct states. You can't measure a silver atom as both spin up and spin down at the same time. Because we can't see two distinct realities simultaneously, there is but one reality. Nature picks a reality so that observations make sense. And this brings us back to our trouble with the operator sigma sub x, spin in the x direction, acting on the spin up vector in the z direction. What does this thing even mean? You can't measure the spin in the x direction and find a quantum state vector that's measured in the z direction. The output of a Stern-Gerlach experiment in the x direction, once observed, is going to be either up or down with respect to the x basis. To really drive this point home, let's do another exercise. Show that the vector, let's call it sigma sub x, which we can think of as something proportional to spin up plus spin down in the z direction. Show that that is an eigenvector of sigma x, that matrix with ones on the off-diagonal terms. What is its eigenvalue? Similarly, let's define sigma x minus, or sigma minus x, as up minus down, in the z direction. This vector here. Show that it is an eigenvector of sigma x. What is its eigenvalue? Finally, normalize both of these vectors, sigma plus or minus x, so that the inner product with themselves is equal to 1. And, for fun, show that they're orthogonal. You might want to do that now. It won't take long. Okay, finally, to make sure that you've understood everything that we just said, let's go back to the simpler case of the two Stern-Gerlach device. We already know what we see. We see an evenly split beam on the final detector screen. Given the last exercise that you just did, you should be able to explain why the beam splits in two mathematically, right? In other words, let's codify it as another exercise, although it should be really quick. Starting with the quantum state vector up, and then measuring that vector's spin in the x direction using sigma sub x. What are the observable states at the end of that measurement? And what are the observable values that are associated to those states? Lots of eigenvectors, lots of eigenvalues. If you understand what we just said here, if you have internalized those math fun facts, then you are well on your way to understanding quantum mechanics as a whole. There are still plenty of new ideas to learn, and there are still a lot of context that we need to give, but the foundation is here. Well done. Now let's get back to that three-machine circuit. Okay, let's revisit our three-device setup. Specifically, we arranged the magnets of the three devices to be in the z direction, the x direction, and then the z direction again. Let's approach this setup from a mathematical point of view. So operationally, the silver atoms that are coming out of the oven, the original beam, are going to have randomly assigned values of alpha and beta. That random vector enters the first device. The first device measures sigma z. It measures the spin in the z direction. So we're going to hit that vector with sigma z. But because we're blocking the output in the down direction, we know that we're observing the spin. Specifically, only the spin up cases are allowed to leave the device. That's our way of doing the measurement. Regardless, because it's a measurement, only an eigenvector is allowed to leave the device, and the only eigenvector that we allowed to leave the device is spin up. So we know as these silver atoms exit the first device, they're in the spin up state. Now these silver atoms enter the second device. We're going to be measuring sigma x in exactly the same capacity. So 1 and 0 gets hit by the operator sigma x, but it doesn't matter because we know that we're only allowing the eigenvalues out of the device that correspond to spin up in the x direction. And if you've done the exercise, you know that that eigenvalue is basically proportional to the vector 1 and 1 times, 1 over the square root of 2. Good. So that is the vector that's leaving the second device. Finally, that vector enters the third device. That device is measuring spin in the z direction. And so it's back to kind of old hat here. We know that the probability of observing a silver atom with this state in the up orientation along the z direction, right, is given by 1 over the square root of 2 squared, alpha squared. That's 1/2, 50%. Similarly, the probability of observing that silver atom in the down orientation as it goes through the final device is 1 over the square root of 2 squared, or beta squared, or 1/2, another 50%. So the beam evenly splits in half. All right, now let's consider the case in question. Let's consider the case where we made an error last time. This is exactly the same setup, except we remove that screen blocking the spin down output of the second device. And then we refocus the up and down beams using kind of a beam merging device, which we make up, and allow the merged beam of silver atoms from the second device to enter the third device. operationally here, what we're not doing is looking to see which direction, which orientation the silver atoms have as they leave the second device. No measurement is made. Let's see how that works mathematically. Mathematically, it starts the same way. Randomly assigned alpha and beta enter the first device, get blocked if they're spin down, only are allowed to exit spin up, so we're making a measurement there. We know that the state entering the second device is going to be 1 and 0. No problem. This state now gets hit by the magnetic field inside the device. That magnetic field is represented here by this matrix, sigma x. Sigma x acts on that vector and flips the spin. So now it's a spin down state. But because we are not actively measuring, we're not looking to see which way that silver atom went, we don't require that an eigenvector exits the device. That state is now allowed to enter the third device, which does again perform a measurement, and that measurement, of course, is in the z direction. So now we have a state that happens to be an eigenstate of the z direction that's 100% down, and so we see that the beam here exiting the final device is pointed 100% in the down direction. There's nothing spin up. Let's contrast that case with the case where we turn off the second device. So there's absolutely no magnetic field in the x direction, in which case we see that the beam is actually pointed 100% up because we've gone from a z eigenstate leaving the first device into a z measuring device in the third device, which again allows only eigenstates of z, but there's only one, and that spits out spin up. To really drive this point home, let's imagine turning off the first device. In this case, the randomly assigned silver atom parameters, alpha and beta, coming from the oven, enter the second device, and no measurement is made. What is happening here? Sigma x, that magnetic field is still there. It's still going to act on this linear combination of up and down states. And it's going to actually flip them. So beta and alpha will be the new vector that exits the second device. As it enters the third device, in this case, what happens? Well, the intensity of the spin-up beam is going to be given by mod beta squared, and the intensity of the spin down beam is going to be given by mod alpha squared, and their relative intensity, if you like, is going to be given by their ratio. But again, it's 50-50 on average because we assume that these are randomly distributed over many, many silver atoms. And so indeed, we can see the difference now. When a measurement takes place, the quantum state vector is affected, and it's affected in a particular way. It's affected in a particular way that selects out an eigenvector. If no measurement takes place, but a magnetic field is still present, that quantum state does get affected, but it only gets affected by the action of that linear operator, by the action of that matrix. That's the key distinction. Because no measurement was performed, we didn't have to observe an eigenvector out of the second device. Finally, we can turn those clickers on in that scenario. So now we are, despite the fact that we're merging the beams, we are actively sensing which direction the silver atoms exit the second device. With the action of those clickers, we are performing a measurement. And because we are performing a measurement, the silver atoms entering the merged beam are either always going to be spin up or spin down with respect to the x direction. Those are the sigma x and sigma minus x states that we discussed in the exercise. And because of that, we know already that both of those states have a 50-50 chance of being observed in either of the z directions. As a result, the beam once again splits in half. Crazy, right? A lot of eigenvectors, a lot of eigenvalues. We will be revisiting these ideas again and again. Finally, to really check to make sure that you understand what's going on, let's finish up with two more exercises. First, let's suppose that we rotate that second device in our setup by an angle theta between the z and x directions. So precisely, let's say that we have a new operator, sigma sub theta, which is given by cosine theta times sigma z plus sine theta times sigma x. So in other words, we've rotated that device. If the clickers are off in this instance, what would you expect to see on the final screen? Specifically, what's the relative intensities of the two final beams, the final spin up and final spin down? And to give you some exposure to playing with eigenvectors and eigenvalues, let's go ahead and turn those clickers on. So now we are measuring which direction the silver atoms are exiting this new rotated device. what is the ratio of the intensities of those final beams in this instance? Okay, and for our last exercise, let's go ahead and insert another kind of one of these mischievous non-measuring Stern-Gerlach devices, so that we'll have Z, X not being measured, Z not being measured, and finally Z measuring towards the final screen. So we're going to merge the beams again one more time, and we're not going to take a look to see which way they went through. How does this affect what happens on the final screen? And just for fun, let's do a part B. Suppose that we take those two internally non-measuring devices and flip them. So in other words, we're going to have Z, then a hidden Z, then a hidden X, and then finally an observing Z. What does the final screen look like in that case? Okay, answers to these exercises, I've already written them up. We will talk about them and how I'll get those to you in a later time. Today was a heavy one. A lot of complicated details, a lot of mathematics, but I'm confident that given, enough views through this video, you'll figure it out. Please continue to ask questions. Dante, thank you for your question that inspired this whole video. I appreciate it. If you have any questions, let me know. If you have any other questions, you can go to the Substack. Go to PassaitinInstitute.substack.com. You can get the app. There's a chat feature in there. I can check that. You can shoot comments down below. You can shoot me an email. You can go to the website, contact me through there. However you want. We'll figure a better way to do this. Just let me know how things are going. I'm curious. Thank you so much for watching. Next time we'll talk a little bit about complex numbers and that kind of stuff. Cool. See you then.